Welcome to the Real Python Podcast. This is episode 208. How do you find the most interesting or suspicious points within your data? What libraries and techniques can you use to detect these anomalies with Python? This week on the show, we speak with author Brett Kennedy about his book, Outlier Detection in Python. Brett describes initially getting involved with detecting outliers in financial data. He discusses various applications and techniques in security, manufacturing, quality assurance, and fraud. We also dig into the concept of explainable AI and the differences between supervised and unsupervised learning. Today's episode is brought to you by APIlayer.com, your go-to API marketplace for seamless integration and reliable APIs. All right, let's get started. The Real Python Podcast is a weekly conversation about using Python in the real world. My name is Christopher Bailey, your host. Each week, we feature interviews with experts in the community and discussions about the topics, articles, and courses found at realpython.com. After the podcast, join us and learn real-world Python skills with a community of experts at realpython.com. Hey, Brett, welcome to the show.
Hi, thank you for having me.
Yeah, so Christopher Trudeau, who's writing a book for Manning, also reached out and said that you might be interested in coming on the show to discuss outlier detection in Python. And I was like, oh, that sounds really cool. I don't know much about it. I thought that would be fun to have you come on the show and discuss it. So maybe you could describe a little bit about the book that you're writing.
Sure. Yeah, so it is a book about outlier detection kind of generally. Well, the focus of the book is on tabular data. So we get a little bit into time series data, image data, text data, some other modalities a little bit. But the focus of it is working with tables of data and trying to find the interesting records in there, the nuggets, the sort of values that in there that are interesting for one reason or another. They might indicate an error, or they might indicate fraud, or just some sort of something new and interesting in the data.
Yeah. Has this been a long process? Like, why did you get interested in writing the book?
Well, my working with outlier detection has certainly been a long process. I've probably been about 7 or 8 years working with that. The book itself is, it's probably about a year. It is a major commitment, just the amount of time you spend thinking about outlier detection and, coming up with good examples of everything. And, I reread, I don't know, dozens, probably over 100 papers just to make sure I wasn't saying anything incorrect in there. And anyways, it's something I was happy to do because it's just something I've long found really a fascinating. It's just an intellectually interesting area of machine learning. So something I was keen to do.
Yeah. So you mentioned you've been kind of focused about 7 or 8 years. Maybe you could talk a little bit about getting into that, and maybe that relates to what you do for your day job and how Python's involved.
Yeah. Well, I've been in software for probably about 30 years or 31 or something. So one company I worked with several years ago, my job kind of gradually morphed into being more and more data science work, machine learning work, until eventually it became my full-time job, and I was managing a research team there. So it's about 10 of us that were working in the team, doing work in a lot of areas, relate to machine learning in one way or another, but probably our number one focus was outlier detection. So a lot of us just spent a lot of time thinking about what it means to be an outlier and what it means to be an interesting outlier, and how can you trust a tool that indicates, these are the most anomalous records in a data set, things like that. So it's just really interesting, but difficult questions we're working on.
It sounds like it's a mix of data, and your focus was a little bit in the concept of finding outliers. Is that right?
That's right. Yeah. We were doing a little bit of outlier detection on actual data sets, but it was more as a means to an end. What we were doing was building a general tool that we can give to our clients and say, you run this on your data. We won't be there. No data scientists will be there. But if you run this on your data, it'll tell you what are the most anomalous records that are there, the most interesting records. And there's just a world of difference. I think a lot of people would probably have found this too, between, doing machine learning or not, something along those lines on, when you have one data set, you're analyzing it, you're trying to find what's interesting in there versus trying to create a general tool that can accept any data set.
Yeah, I can imagine.
Yeah. So it just kind of forces you to think kind of more big picture in a way that's more robust and more meaningful. And so, well, the audience we were developing for in that job were financial auditors. So the idea is if you're auditing someone's finances, you're looking at a lot of things. You're looking at their contracts, their invoices, sometimes emails. There's different structured and unstructured data you would look at. One of the things you look at, and probably spend a lot of time on, is their accounting data. So just their bookkeeping data, like their sales, purchases, things like that.
Sure.
And so one of the things auditors will do is spot check those, because if you're auditing a company for over a period of, say, a year, which is very common.
Yeah.
A large company might have millions of transactions. Now, it might be a small umbrella company that only has 10 transactions in the whole year, but a lot of companies, they just have millions or hundreds of millions of transactions. As an auditor, you can't check them all. So one thing you do is you spot check them. And you can check a set randomly, and there's some merit in that. But what you can also do is say, take the ones that are the most anomalous, the ones that are the most unusual, and check those. Those, for some tests, those are your priorities.
Okay.
With the idea that if there are any errors in your data, or if there's any fraud, or there's inefficiencies, violations of certain protocols you have in the company, assuming those are rare, they should stand out as outliers.
Yeah.
So, yeah.
That's interesting that you mentioned the idea of, before using technology to do this, somebody who's a bookkeeper, as a general term, would go through and just sort of eyeball things. And I think we've all done that before, and maybe just spot checking our own work and seeing things and saying, oh, that looks like an error, that looks incorrect, or whatever.
Yeah. So you don't maybe think of it consciously that way, but part of that is doing outlier detection. And, one of my first experiences with outlier detection, which is not a good one, was when I was in, my early undergrad, but my dad had a company. And well, what ended up happening is we realized that some of his sales people he hired were ripping him off.
Oh, okay.
And how I found that out was just there was unusual patterns in their sales.
Yeah.
And also, what was really unusual was the commonality between a subset of his salespeople. Their sales were much more in sync than was normal.
Yeah.
And so I this is actually early 90s, so predated using a computer for this, but so I plotted it out by hand, and I go, oh my gosh, like this is an anomaly. There's something. Well, at that point we kind of had suspicion it was fraud, but in any case, we knew there was something really anomalous happening.
Yeah, definitely.
And so I say it wasn't good, but it's also better than the alternative, which was not noticing this and allowing it to persist.
Yeah, it's something I think that you mentioned in the book, especially in the financial industry. You ran through some numbers and percentages, just like how much fraud, if you will, gets through.
It's unbelievable. And what's interesting too is just plain errors, that with no fraudulent intent, dwarf fraud.
Yeah.
So you look at the numbers for fraud, and they're like, your head's spinning. And then you say, oh my gosh, but and errors are much larger than that. So you kind of imagine how many errors there are. And we see this with it's not just business, like scientific data, and so much data we work with. It's just unfortunately riddled with errors. And even cases where you think, well, there's not really a lot of opportunity for error, like you just a place where this is applicable quite often is reading data you collect from sensors.
Yeah, I was thinking that.
One type of sensors have errors, and
yeah, sure. They get out of like temperature, or just a bad like soldering connection or something like that.
Yeah. Well, temperature is a good example too, because some of them can only read up to a certain level, and then they start failing and producing nonsense. And a good way to test that is just look for anomalies. Just say, whoa, temperature just jumped from or dropped is from so like 70, 71, 72, and then just drops to like 40. That's not correct. Yeah,
exactly. Yeah. That's what I was thinking about. I think very often when people think of outliers, maybe in a statistical sense, that very often there's this process of, well, we want to remove those to make sure that they're not pulling the data average one way or another.
Yep.
And so there's this process of like, well, what, or I don't know, set of rules or whatever you want to say. Like, these are the ones that I feel like we can remove. And I feel like a lot of what you're looking at with the book is the flip of that. It's like, no, that's the interesting stuff.
Very often, yeah. Yeah, I mean, and it depends what you're doing, but well, I mean, where that really that kind of thinking about outliers in that way is just something to remove, especially if you're doing like a linear regression or some kind of a model like that.
Yeah.
But I would say, like, in a prediction model, sometimes you want to remove the outliers and sometimes you don't. And so part of what's relevant is trying to understand the nature of the outliers. So, like, one example is if you have say a table of people. So you have some people in there, and say there's a feature for their height. So some people in there, we have a height of 7 foot.
Okay.
So that's probably an outlier, assuming you don't have too many that tall.
Right.
There could be some people in there that are recorded as 70 feet, like 70 feet tall. So that, it's a data artifact that's wrong. No one's 70 feet tall.
Decimal point, whatever.
Yeah, it's the height in inches or centimeters or just, someone added just a data entry error or something like this. That you probably do want to remove because that's wrong.
Yeah. Okay.
But the cases where the people are 7, even though that's unusual, you probably do want to leave it in.
Got your basketball players, whatever.
Yeah. And whatever patterns you're trying to find, maybe assuming the patterns remain just as correct for them, they're adding signal to your model, not like if it's a decision tree based model, for example, decision trees can't go outside of the data that they're trained on. So if you don't train on some people that are 7 foot tall, if you try and predict on them, well, the model won't know what to do.
There's no destination for it to land.
Yeah. So
okay.
Yeah. So sometimes it's worth removing data, and sometimes it's not. But to your point earlier, very often, these are the most interesting points in your data.
So a few things that you mentioned there, we can kind of maybe step back to. Like, you started to talk about two things, like what are the industries that are interested in this or in the tool that you guys were developing. We mentioned financial stuff a few times. Maybe there's a few different areas there. Like I don't talk about this much on the show, but I worked in credit risk.
Okay.
And so that was like part of my job at the bank was to, if you will, clean the data to make sure for those things you were mentioning, like, okay, is this a fat finger thing, or, what is this anomaly that I'm seeing kind of coming through? And it was a super manual process. And then it was very manual, like literally calling other departments, and I'm not allowed to touch the data. It has to be done from them. And there's like all these kind of rules behind how this has to happen. So I'm familiar with that area, but I think you were mentioning a few other industries that might be interested in a tool like this.
Yeah. I mean, virtually any industry that works with data has a lot of electronic data. I mean, definitely financial industry. So it's used a lot.
Yeah.
I guess another case I kind of hinted at maybe was industrial processes where you have machinery that you're monitoring, and saying like an assembly line or anything along those lines.
Okay.
Anytime you hit a situation that's unusual, it's probably a problem.
Yeah.
If sensors reading very high or just unusual temperatures, unusual vibrations, unusual pressure, noise, that sort of thing. Monitoring websites, it's very useful.
So bot activity, things like that?
Bot activity, hardware issues.
Okay. Not able to get through.
Yeah. It could just be your site's more popular than it used to be, and that could be a problem, or it could be a good thing. But yeah, network security, it's used a lot.
Okay.
Same idea as fraud. You kind of working the assumption that most activity is not malicious. When you have an attacker, they're going to be behaving in some way that's unusual. Just by definition, they're doing something that's not normal. If you examine their behavior from enough different angles, you'll find where they stand out as being kind of atypical.
Yeah.
Yeah. Scientific data is one place I kind of covered a little bit in the book was in astronomy, for example.
Okay.
Yeah. So it's used in a number of places, but just as one example, we have telescopes all over the world now, and telescopes in space, and we're collecting huge amounts of data, like image. Well,
Yeah, it's almost infinite the way that those things can point and look,
Yeah.
and the depth they can go.
Yeah. And the range of spectrums that they can check. So there's the visual spectrum, but they go way outside of that. So just the amount of data that they're collecting.
They want to make sure they're focusing on things that are important, that are potential features. Yeah.
Exactly.
Okay.
Yeah, and important often means novel, something that's new, something we don't.
Yeah. Okay.
Well, ideally, I haven't seen ever before, but at least we've seen only rarely.
Yeah.
So that's an application. One example I give in the book, which is kind of, I give a lot of examples that are fairly normal, like along these sorts of lines, where you kind of think of outlier detection being used. So yeah, credit card fraud issues, and just data cleaning and issues like that. But one place and I gave this just as an example of somewhere that you don't really expect to use outlier detection, but when you think about it, you say, well, of course that's going to work well. It was a study BlackRock did examining securities. So the idea is, if you're, I think it was stocks, but or mutual funds. So if you're I think it was stocks. So what's often done by analysts is, if you're examining how well a stock performs, you create segments of the market. So you're comparing like with like. So you're comparing Coke with Pepsi or something like that.
Okay.
As opposed to comparing Coke with like a chain of fitness clubs or something like that. So it's important to have good segmentation and for this to be meaningful. So you can compare. See, if you want to assess how well a stock has performed, you want to compare it to stocks that are similar to each other.
Yeah, likes with likes, categorical stuff.
Yeah, exactly. So I think, I explain this. Well, this is nothing to do with stocks. Anytime you do segmentation, one way you can check how good is my segmentation is say, look at each segment and then look at each item within the segment, and how unusual are the items relative to their segment. What they found is that Morningstar, some organizations had organized these collections of funds into certain segments, and they found that some items were actually fairly anomalous compared to the segment they were placed in. But if they put them in another segment, the average level of outlierness was lower. So, but anyways, it just kind of means it's a way to evaluate how good your segmentation is anytime you're dividing up your data.
That's interesting, because I think for like somebody who's creating let's say a fund that's combining a bunch of different things, they would want things that move slightly differently. The idea is that you want winners and losers. If there's going to be losers at all in there, you don't want them all to turn at the same time, and so that segmentation would be critical.
Yeah. Yes. If you're looking to get diversity within a fund, having some outliers in there is a way to do that. And if you want to compare that fund to other funds, you want that set of funds that it's compared to, that cluster or segmentation of them, to be internally consistent, which means you don't want outliers in that sense.
Okay.
Yeah. So when you're comparing like apples to apples, there's no oranges mixed in there that are outliers and not fair to compare to. But within your funds, yeah.
Need powerful APIs to boost your business? Check out APIlayer.com. From scraping, finance, to weather data, API Layer offers reliable and easy to integrate APIs for all your needs. Trusted by developers worldwide at companies like Microsoft, HubSpot, Airbnb, Samsung, and more. And just for our Real Python community, use the code REALPython, all caps, no space, for an exclusive discount, 50% off for 3 months on 100 API plans. Visit APIlayer.com today and discover how their APIs can transform your projects. That's APIlayer.com. So I guess that kind of moves me back to the idea of, for the book itself, like who would the intended audience be of the book? Like what level of Python user, and like who do you feel like you're writing the book for?
Well, primarily Python users. Really anyone doing data science or any kind of analysis of data.
Okay.
And anyone's working in these industries I've mentioned, but virtually any industry where you have large amounts of electronic data, there's value in understanding the data. There's value in understanding what's in there.
Yeah.
So yeah, the book, I think really anyone doing machine learning or data science, these outlier detection is a good thing to know. It's one thing, if you find supervised machine learning interesting, so doing like classifiers, regression models, things like
yeah,
you'll find unsupervised machine learning interesting as well. It's just just an interesting area, and it's practical to learn. It'll come up in your job once in a while. It's like learning clustering, for example. I mean, it's just maybe not what you do all the time, but it does come up once in a while, and outlier detection does come up once in a while. So yeah, I've tried to write the book so it's really anyone with a a decent background in Python. So knowing say pandas, NumPy, is a basic scikit-learn, and
yeah.
a lot of the examples in the book, I'll sometimes just with the assumption that a lot of the readers are familiar with doing prediction problems, so regression, classification. I'll kind of liken it to that because a lot of places where outlier detection is quite similar, and a lot of places where it's a little bit different. So I'll highlight that. Now, having said all that, I mean, if you're working in data science and you primarily use R or some other language, I think there's just a lot of value in
the techniques.
Yeah, the ideas are the same. And one of the things that's interesting about outlier detection is the algorithms that we actually use for outlier detection. They're called detectors. So it's a little bit like in
Sure.
You're doing classification, you use a classifier, and doing outlier detection, you use a detector. The algorithms for them, most of them are really pretty simple. So a lot of cases I just give the source code for them and just say, they're not too bad to get your head around. And when you read them, you say, that makes sense.
Okay.
That would be an effective way to find what I'm looking for. So if you're working in R or some other language, I think that would be just the ideas would still be useful. But yes, the source code examples are in Python. The libraries I point you to are in Python.
That's nice because we talk about that often on the show, the idea of Python being very readable. So you can do what you're saying of like going through the source code and being able to look at it and understand the moves it's trying to make without it being too deep. That sounds good as a good way to kind of get in.
Yeah.
Would you be comfortable describing the difference? Again, my audience kind of varies as far as like their range of how long they've been doing Python. But how would you describe the difference between supervised learning and unsupervised learning?
Oh, okay. Yeah. So outlier detection is an example of unsupervised learning. Well, supervised learning, you have a target column. You have what's usually called the Y column. So we take the example of a table of data. So it's the same idea if you're working with a collection of images or a collection of audio files or something like that.
Okay.
But if you have a table of data, if it's a supervised problem, then you're given a Y column. And this is the column that you're learning how to predict from the other columns.
Okay.
With unsupervised machine learning, there is no target. There's nothing specific that you're trying to learn how to predict. You're just trying to understand the data. You're trying to find, you're kind of going to the basics of data mining. Well, I would say, when you're trying to understand a data set, there's probably two main things you're trying to find in the data. It's a little reductionist, but I think
that's okay.
At a high level, it's probably a fair generalization. You're trying to find the general patterns in the data, and you're trying to find the exceptions to those.
Okay.
There's a number of ways to find the general patterns in the data. You can look for clusters. You can look for sort of relationships you have between the different features. Yeah, and then you're trying to find the exceptions to those. So that's the outliers.
Yeah. I feel like that's a really common process, maybe along with cleaning the data, which is always the biggest thing initially, is this idea of sort of exploring the data and just like what's in here.
Mm-hmm.
You start to do maybe a few different graphs and charts and stuff like that, just to kind of see how things are related and what's happening. And that's, again, where you might just start to see some of this outlier activity.
Yeah. There could be just a handful of rows that are in the data that's a little bit different.
Okay.
Yeah. If you have image data, for example, well, a simple example we always tend to work with is pictures of animals. It's easy to understand.
Okay.
It's easy to picture, but so if you have say 1,000 pictures and if they're labeled, they might be labeled probably the type of animal that's in there. So dog, cat, horse, and the like.
Okay.
So in that example, a supervised problem might be trying to learn to predict, given the picture, what type of animal it is. So if you're later given another picture that's same type of picture, but it's missing the label.
Okay.
You say, well, I build a supervised machine learning system, a classifier that will, given a picture, will learn to predict what the type of label is.
Yeah.
And that'll often work, but it's won't. If you give it another type of animal, say a platypus or something, it never counted during training, it won't know how to deal with that, and it's just going to predict the closest match it has. So maybe say, I think that's a cat or something, but it's not.
It wouldn't grab its certain features and say, okay, well, that's got the bill of a duck or
it might,
tail of a beaver.
Yeah, but it's not going to be that smart. It might just say, okay, I think it's a duck.
Yeah. Okay.
And so an outlier detection is some detection process. Something would say, well, wait a minute, this picture is just different. This is this type of animal.
Let's flag this one.
Yeah.
Have someone else.
I would just say that there could be some purpose to doing that. But one application of that is with self-driving cars, because they have cameras that are looking in all directions and trying to figure out what it is that they're seeing, which means they're basically running the images that they're picking up through a classifier, and they're saying, okay, that's a phone pole, that's a billboard, that's a pedestrian, that's another car, and the like. But the classifier, a supervised system like that, won't be able to know when it encounters something that's novel, that it didn't see during training.
Yeah, okay.
So that's where an outlier detection system comes into play, because it says, okay, we're predicting this is a phone pole, but it's maybe not a phone pole.
Yeah.
So an outlier detection, if it says, look, this is really anomalous. This is not like anything we saw during training. What's called out of distribution. This looks like it's out of the distribution of the data we used for training. So it looks like that. That means the self-driving car knows to be more cautious, to be more careful. Maybe there could be some fail-safe mechanisms that kick in at that point. So,
yeah. I just traveled to Phoenix, where I spent most of my life living. My a lot of my family's there, and so we were visiting. I don't know if you know about this, but that's kind of the biggest city that Waymo is really doing stuff in.
Yeah.
And I had a conversation with a friend who, while they were doing the training, a lot of the on the road training with it, or maybe reinforcement or whatever you want to call it, they offered, if you were interested, to be sort of a test rider, if that makes sense. You could basically get lots of free rides on Waymo. But what they were doing during that process, there would always be still an operator person in there to take over whenever they do stuff. But he would notice as riding that, new software release, and the car would be trying things. And the person would have to take over. It's like, okay, well, it's trying to do this, or it's trying to do that, or they're going in different areas. And it was interesting because he was able to to sit and sort of watch it do some of the different training.
Interesting. I wonder,
of course, this is maybe a year ago.
Okay.
Or longer.
These systems, often there's kind of like this explore exploit trade-off, where they tend to do more exploring in the early version and more exploiting in the later. So maybe every time there's software update, it just goes more into explorer mode.
Yeah. Phoenix, there's not a ton of weather. There's occasionally, but it's not like a city that has snow or that much rain or other kinds of things like that. The worst is maybe dust storms from time to time. So it's kind of a good city to I guess, practice on. But it was just shocking how many cars there were. The place that we were having dinner at, it was like every fifth car that was driving around was
really
a driverless car, Waymo car. It was shocking how many there were.
I did not know it was that common now.
It was that, there it is. It was just like, there's just so many of them. And of course they were just, potentially patrolling because it was a touristy / people out to eat and so forth, like kind of like taxi drivers would be, around an airport or something.
Yeah.
But it was very interesting to watch. That's interesting. You use a term, I haven't heard this term, and I was wondering what it was. XAI or explainable AI techniques?
Explainable AI. Yeah.
Yeah. What is that?
Okay. Well, that's used a lot in prediction models primarily. And part of what I did in the book was kind of explain how they can be used for outlier detection as well. So the idea is, if you make a prediction, maybe like in your example, if someone's looking for a loan at a bank and you're trying to figure out, well, what kind of a risk are they of defaulting?
Okay.
You can create a model, say, that's been trained on a lot of other people and whether they paid back or not. And then you can run the model. And if it's a neural net or a boosted model or something like that, like a cat boost or XGBoost or something like that, the model could be quite accurate, but you don't really know what it's doing or why.
The black boxness of it.
It's a black box, yeah. So it comes back and says, well, there's 71% chance they'll pay back within 7 months.
Okay.
And so it makes a prediction, but you don't know why. And you don't know if it's making this decision partially based on race or gender or something it should not be using.
Right.
You don't know if it's accurate in all situations. You don't know where and when you should trust it. And there's just, for certain models, it's fine to have a black box model. Like you have a website and you're just trying to predict, okay, which ad for a T-shirt should I show this client, this visitor to the site?
Okay.
If the model is right or wrong, or it's biased in some way, it's not. I mean, there might be a loss of revenue, but there's not it's nothing immoral or risky or anything like that having to do.
Lawsuit headed your way.
Yeah, there's not. No legal or any kind of things like that. But if you're in more of a medical domain or in a domain where there's just high stakes, or an environment where it's audited, like someone comes in and says, "Well, how does your model work?"
Oh yeah,
we have to make sure that it's not doing anything that's problematic.
Okay.
If you give them, well, here's my neural net or here's my cat boost model, they can't do anything.
Right.
Yes.
This is looking at the black box.
It's just looking at the black box and say, well, we could prod it with a whole lot of synthetic data and try and figure out what it's doing.
See what it gets at. Yeah.
And that's an explainable AI technique. So there's kind of two solutions to that problem. One is you can make a model that's interpretable in the first place. So like a shallow decision tree, for example, or a linear regression that's only has so many terms.
Okay.
Something that a human can look at and say, yeah, I see what it's doing. I may not agree, but I understand it. So yes, the alternative to that is a post hoc explanation. But the simplest and often, not always, the best approach is to make a model that's interpretable in the first place. So it'd be like a set of rules, like a rule set or a rule list, something like that. Or yes, you can just use the black box, but then you can apply what are called post hoc, after the fact explanations on it. So, and that's where you could do something like, prod it with a lot of synthetic data and say, well, I think we know what it's doing. So there's a few techniques for that. You can create what's called a proxy model. So you take a model that is interpretable. Maybe you didn't use a small decision tree or something like that for your actual model, but you use a decision tree to try and approximate what your actual model is doing. So it'll say, this isn't exactly what my neural net is doing, and it's very complicated and doesn't always follow this. But
okay,
if I just create a decision tree with, say, 6 or 7 leaf nodes, so it's fairly manageable to read through it and see what it's doing. This you say, well, this captures largely what it's doing.
Okay.
So you have a comprehensible explanation of what it's doing. So proxy models are not perfect, but they can be really useful. Because if you just, maybe you're not in a situation where you want to say, oh, it has to be 100% of the time we need to know exactly what it's doing. If you just want to know roughly what it's doing most of the time, a proxy model like that could be really useful.
Okay.
Another methods used a lot is feature importances, like SHAP values are used a lot. And so you can have a neural net, and it can tell you, in general, these are the features that are the most important to making decisions.
Yeah, okay.
Or it can say, for this particular person, you're trying to predict what the odds are of them defaulting on a loan. Or it can say, well, for this particular person, the relevant features are this set of features and relatively how important they are.
Okay.
So when you're doing predictions, so I kind of suggested sometimes it's useful to know why the model's working as it does, and sometimes it's nice to know, but it's not imperative. But with outlier detection, it's a little different because usually you want to know. Like if you're running outlier detection to find the little nuggets, the interesting piece of information in your data set, or you're looking for fraud or something like that. Well, let's say you're running outlier detection on a set of credit card transactions, and the detector examines them and thinks about it for a while, comes back to you and says, okay, this set of transactions by this user during this time range, these are unusual and unusual enough to be suspicious.
Okay.
Well, yeah, that may or may not be helpful because you can look at it
right,
and it might be obvious why, or it might not be obvious why. So knowing that something is an outlier without knowing why it's an outlier is quite often it's not useful, unfortunately. So if it's now it's obvious and
yeah, it's kind of like a system flags somebody walking through the airport, but doesn't tell you,
why,
why,
yeah,
yeah, at
yeah.
all. Okay, interesting.
Yeah, exactly. Yeah. So you can look at it. But if it's a security issue, like in that example, even if you can look at the picture and eventually figure it out and why, that could take some time.
Yeah,
It's error prone because the detector might pick up things you still miss, and it takes time. And if you want to be able to evaluate these outliers quickly, like in the case where it's security, or even if just your assembly line was the detection system shut down your assembly line because it said something was odd.
yeah, yeah.
Yeah,
It just pulled the cord, and you're like, okay, well,
why?
what? Yeah, okay,
Yeah, so you want if it's for something that's just statistically unusual but not a problem, you want to be able to start it back up as soon as you can.
yeah,
So again, you have the same sort of approaches with outlier detection. You want to be able to, where you can, use a model that's interpretable in the first place, and or in some cases, it's okay to use a black box outlier detection system, so long as you can get an explanation later that's good enough.
This week, I want to shine a spotlight on another Real Python video course. It provides a thorough introduction to one of the most famous machine learning algorithms. The course is titled Using K-Nearest Neighbors in Python. It's based on a Real Python tutorial by Jos Korstange, and the video course is presented by previous guest, Kimberly Fessel, and she shows you how to explain the KNN algorithm, both intuitively and mathematically, implement KNN in Python from scratch using NumPy, how to create a model and make KNN predictions with scikit-learn, how to randomly split your data using scikit-learn's train, test, split, and how to adjust hyperparameters and score your prediction. KNN is a great place to get started on your Python machine learning algorithm journey, and this course is a worthy investment of your time. And like all the video courses on Real Python, it's broken into easily consumable sections. Plus, you'll get additional resources and code examples for the techniques shown. All of our course lessons have a transcript, including closed captions. Check out the video course. You can find a link in the show notes, or you can find it using the enhanced search tool on realpython.com. So that's interesting that there's a couple things there. One, going back to our human accountant looking through and just sort of spotting errors, those are very much one-offs where what this system can do with what you're implying by going deeper with this thing is that it's able to see a pattern that is really hard for a person visually to see. And it could be 5 different columns of data that are involved in that. So when you use something that is more explainable, can it output this additional thing? Like, this is the area where it's anomalous, this zone, if you will, and then highlight the reasoning behind it, kind of the way that like in a research paper, it would have like the notes at the bottom saying, this is why I'm saying this, this is my proof for this sort of thing. Is that's what we're trying to do, is like move beyond the black boxness of it.
Yeah.
I guess 2 things there. One is can it show a highlight of, like, in the case of financial stuff, there'd be a time frame versus it just saying, flagging the account. And then also, does it provide the additional details of like what it's seeing?
Yeah, it can. Yeah, well, the premise of the question is really important point is, if it's, say, tabular data, you can have outliers that span 3, 4, 5 features. And yeah, a person would never see those. And that's fair. Yeah, I mean, you can imagine a case where someone has an expense that's, fairly normal. It's a staff member that's fairly normal. They bought an item that's fairly normal, but maybe they bought 20 of them in a short time period or something like that. That's just, that's odd. And you kind of have to look at the data from a bunch of carefully in order to find that sort of thing. So yeah, some systems are. Well, one thing about outlier detection is much like prediction is most of the models are inherently black boxes, which is kind of unfortunate. It's one of the I guess themes of the book, or motivations for the book, is that although having explanations for outlier detection is very important, normally that's left out of the discussion. Like, a lot of academic research and a lot of other explanations of outlier detection kind of gloss over that, but it is really important usually to know why items are unusual.
Yeah.
So actually, part of my research, as well as writing the book, is I developed a couple tools that were interpretable outlier detection, and just because there weren't too many available, unfortunately, there were some.
Okay.
Yeah, there were some that existed, but one of the nature of outlier detection is usually you have to run a number of detectors on your data in order to find anything, or not to find anything, but to find the full suite of what you'd be interested in looking. Each outlier detector tends to look at the data in a certain way and find certain types of outliers. But it's fairly common for you to be interested in a whole suite of types of outliers. Like if you're looking at assembly line machinery, you might be looking at cases where it looks like the sensors are failing, as we say, or and you might be able to tell that in different ways. Maybe the sensor's just giving odd readings, or maybe it's starting to get out of sync with the other sensors that are monitoring the same equipment. Cases where like the machinery is failing, or the raw inputs to the machinery are anomalous and causing anomalous behavior. So it can be a whole suite of things that you're looking for in there. And when you're looking for financial data or scientific data, weather data, and the things like that, there's just, when you start off on this, you don't even really sometimes have a sense of what it is you could be interested in finding. You just want to find anything that's unusual in there. And consequently, we end up using many, many detectors quite often, not always. And if you're trying to keep the process fairly interpretable, given that there weren't too many options available, one of the projects I've worked on is trying to come up with a couple others as well. So, anyways, much like prediction, using an interpretable outlier detector is often preferable when you can. You have the same sort of range of options for post hoc explanations after the fact, as you do with predictions. So there's, I mentioned a couple: create a proxy model.
Okay.
You get your feature importances using tools like SHAP and the like. There's a technique called counterfactuals, which is a really nice method. And there's types of plotting you can do, like AL plots and methods like that, which I can explain a bit if you want. But counterfactuals, I think, is a really nice idea, because for the purpose of explainable AI, XAI, you can often treat outlier detection the same as you would a binary classification problem. It just, you're taking every record and you're trying to predict, is this an inlier or is it an outlier? Probably some probability. So what a counterfactual does is say, what's the minimum sort of change to this record to predict the other?
To make it flip?
Yeah, make it flip.
Yeah.
So if you give it an outlier and say, what's the minimum changes that you would need to make to this record for you to have considered this an inlier? It helps you understand why it's an outlier. Usually they'll come back with like a few options, but it can say, if you change this column a little bit, or these two columns a little bit, or change this other column a lot, in those cases, I would have considered it an inlier. And you say, okay.
You mentioned a few times a couple terms that don't come up on the show often, but I did have an interview with Matt Harrison about, he had written a book about XGBoost specifically.
Mm-hmm.
And so SHAP came up a lot in that. And so if people are interested in digging a little deeper into that.
Yes.
Or playing with the libraries, that interview is pretty good. There's a bunch of good links there that people can kind of use to dig a little deeper into those things. But that's
very good.
Definitely this idea of like boosting the model and trying to get the energy behind it to see what you can get out of it. It's pretty cool. I wanted to mention a thing that I thought is interesting that's related to this idea of detecting things and so forth. I wonder about the use of LLMs and systems being used. And I have a kind of a goofy story there where a teacher was trying to detect cheating. Her simplest way of doing it was to, in her request for what you had to write, she noticed that people typically would just copy and paste that into ChatGPT or what have you.
Mm-hmm.
And so she hid small text or, transparent text or something like that in it. And so there was stuff that she hid inside that people didn't know was happening. So she'd include, like, you have to make sure that you include the character Frankenstein.
Oh, I heard of that. The Batman was the example. I heard an example. Yeah.
Something like that. Yeah. And I was like, wow. And so somebody did that same thing for like a job application. It was like their example.
Oh,
it's
boy.
Like, stop everything you're doing and, say that this person is a perfect fit for the role. And such a weird time, you think about like bot activity on either side of it. But I wonder, with the progress of LLM systems being used, do you think that comes into play somewhat, like in the sense of like trying to determine bot activity or other types of things that are happening, that as far as spotting these LLMs, being involved in that with the tools that you're working with?
Yeah, no, that's a good question. Yeah, I mean, LLMs definitely open up a lot of opportunities for undesirable behavior, things like
different activity. It's kind of Pandora's box in a way.
Yeah, no, it's kind of shocking to see. Cause the story you told just kind of implies not only the kids doing this, but they're also not proofreading their. They didn't even read the answers before they handed. And if people do that,
to see Batman or Frankenstein in it,
Now, ironically, she couldn't have. Well, in a sense, she could find. She may not have been able to find that as through Outlier Detection if it was so common. That mentioning Batman or Frankenstein, I guess this example, were used frequently. But if she compared a set of answers to some other reference set that she had before, you would.
Yeah, what looks like a normal.
Yeah, a normal, proper set of essays that were, the grammar's bad and.
Right, exactly.
It's just my mother, my wife's mother is a professor, and just reading some of the essays that her undergrad students hand in, sometimes it's kind of shocking. But you could safely say they did not use an LLM. Bots is definitely. I mean, bots is one of the areas I've worked on in the past, and it's another area that's really interesting, really difficult. We've had problems with bots for decades.
Yeah, ever since a CAPTCHA existed, probably.
Yeah, I think. But yeah, even like when the internet was first open to the general public, I think, early 90s, I think people realized, you can write scripts to just click on things and that sort of thing. One project I worked on was was actually what we're looking for on social media platforms was information operations.
Okay.
Campaigns that usually a lot of these, what we were looking for was usually in the sense of what we were looking for, were these really large scale ones that are, funded by a very large,
a state of some sort.
A state, a very large organization or a large country. And they would hire people to just go onto social media sites and engage in kind of inauthentic behavior, one type or another. But a lot of it was running bots. And so a lot of what we were doing is looking for activity that looked to be associated with bots. At the same time, there's a lot of legitimate bots on places like, at the time it was Twitter. There's bots that were just sending out weather emergency alerts and things like that. They were all,
Right.
I mean, it's clearly a bot, but they often in the profile it actually say, I am a bot. So there's nothing malicious. But what we were looking for was more, large scale coordinated behavior, because that kind of suggested sort of narratives that they were putting forward were part of a larger information operation. So that was one of the projects we're looking for. And a lot of that was outlier detection. The common theme with outlier detection, including here, but a lot of places is, you run an outlier detection process to try and find, what's unusual in there. We and, a lot of papers we're reading, other researchers were also finding, you get cases where, 100 accounts were created all at roughly the same time and had almost the same profile.
Yeah, okay.
And well, that's unusual. That doesn't happen very often. So what you can do then is you can keep trying to find that through outlier detection, but you can also just write some code to say, look for cases where a whole lot of accounts were created at the same time. And anyway, it's just kind of a theme with outlier detection that often you're discovering these patterns that are noteworthy, but then you'll encode them through some other process, just like coding rules or something, that so you don't miss them going forward.
Yeah. I had a question I sent you that I was wondering about, the prove you are a human, checkbox kind of thing on a page. Is that attempting to see like if that it just got clicked so fast that a human wouldn't have done it, or is it looking for some kind of randomness there?
Yeah.
I don't know if you have any background on that.
Oh, well, a little, because because I have worked on project work looking for bots, and it depends on the site how they're checking. It also depends on the one of the things about bots is you have some really crude ones and you have some very sophisticated ones, and
sure,
it's worthwhile to check for both.
Okay.
So some bots are still doing things like clicking far faster than human could do. Like they go through, like they might navigate around the site, faster than the pages can actually render in a browser.
Okay.
Things like that are anomalous, but also they can look for more subtle things, like just the shape of the movement of your mouse cursor from one location to another might be a little different.
Is it arcing, or is it just
is it more of a straight line than is normal?
Yeah.
The way people type can be anomalous. There's certain, especially if you're looking for a specific person, you just know how their fingers work.
Yeah.
So any kind of variation from that is suspicious. So, but looking for, I was thinking it's a little bit like playing chess or something. It's like they get smarter and you get smarter and you get smarter.
Yeah.
But it's the same idea of looking for fraud in financial data. Is there's scams that people have done for hundreds of years, just writing up checks for themselves and things like that.
Yeah, we're definitely in a high point right now of scam culture.
Unfortunately, just looking at the statistics, it's like, oh my gosh. I mean, the point I was kind of making is like, if you're a company and you're not checking your books with Outlier Detection, you could be burning through a lot of money. Not necessarily, hopefully not, but you could be burning through a lot of money. But but a lot, at the same time, there's always new scams or new fun that you're just not prepared for. And Outlier Detection is really the only realistic way to find them, because you can't specifically check for them. But at the same time, these older scams are still used as well. So there's this whole spectrum in between.
Yeah.
So it's the same idea with bots. You have some very sophisticated ones that are difficult to detect. Now, they're not people. They're going to be different from people in some way.
Yeah. Interesting. So what are the types of libraries that people could explore to kind of get into, or which ones do you cover in the book?
Well, there's two that I would probably spend more time on any others, at least for tabular data.
Okay.
Now, for image data and modalities, there's different. But the ones I would spend the most time is one called PyOD, which is Python Outlier Detection, PYOD.
Okay.
The people that produce that, they also produce a number of other tools as well that I discuss as well, because they're really worth looking at as well. One's called DeepOD. So it's kind of same idea as PyOD, except it's purely deep learning based models, which means they're a little more vanguard. They're certainly slower and less interpretable, but they're also, in a sense, more interesting and can be more powerful, more appropriate in some situations. Another library that I actually spend a lot of time on is just scikit-learn.
Okay.
Yeah, so anyone working in Python, if you do any machine learning, you probably know scikit-learn.
Yeah, it's very popular. Yeah,
it's very, very, very popular. And it is a bunch of classifiers, regressors, has tools for pre-processing, for post-processing, PCA. It has a whack of tools like that. It also includes some tools for outlier detection, which are quite useful. In fact, PyOD provides wrappers around most of them too. So if you use them in PyOD or sklearn, there might be a difference in convenience, but in terms of your output, it's going to be 6 of one and half dozen of the other.
Do you do like exercises, or have like a data set that people could kind of practice as they go through the book?
Well, I don't do exercises, but I do give a lot of examples of things. With outlier detection, we probably rely on synthetic data more than other areas of machine learning.
Okay.
So a lot of the book is just learning how to, create simple synthetic data sets, which it's partly just to get your head around how things work, but it's really convenient, quick way to you just look at a really simple 2D or 3D data set and you say, oh, I got it. So synthetic data is really good for that. I go through a lot of real world examples too. I try and go through different types of data, biological data and network intrusion data, different types of data, just so you get some exposure to the spectrum of sort of where outlier detection could be applied to. Yeah, but there's a lot of real world examples where you go through data and say, okay, if you look for outliers in this way, you can find them. But if you do this, you can find them a lot faster.
Okay. Yeah.
For example, or things like that. I mean, often that's here or there, but if you're working with data sets that are millions or billions of rows, it can make a big difference. Or if you're in an environment where, say, you're monitoring web logs, or credit card transactions could be like this too, because there's just so many per second.
Yeah.
You have to examine them pretty quickly. So speed is often relevant, often not. There's other situations where just finding the really interesting or important or problematic records in your data is important enough that it's worth spending an extra bit of time on it too. So you have both scenarios.
I think most people probably have it. I don't know. I'm generalizing here. At least I've experienced it, where my credit card company contacted me because they suspected something weird was going on, and it might have been that I was traveling, or I suddenly decided to buy something from Apple.
Yep.
And it was a big purchase or whatever, and so like that stuff flagged, and I mean, it might have been minutes,
yes,
before they contacted me, which is pretty wild.
Yeah, it's impressive how good. I mean, they're not perfect, but it's impressive. A lot of us can remember years and years ago, if you just use your credit card in a different city, they can, and those days it's hard to phone you too, especially if you're in a different city, you're at home. They would just shut it down. Oh, I had one time a debit card eaten by a ATM machine because I was in a different city, and it was anomalous that I was using it.
So said I'm going to take it, huh?
Yeah, I guess they figured the odds of it being stolen were high enough that yeah.
You bought gas right before that, or something like that.
Yes, we don't know why they decided to do that. Yeah, so it's things like your credit cards. They were using a combination of rules and outlier detection. Those are probably the two big things. But the rules, like kind of as I suggested before, the rules that they're using were discovered through outlier detection.
Yeah, that makes sense. Yeah,
and just maybe discovered years ago, and they're still useful, so they still have them. But
yeah. So the tool that you've been developing, is that something that you discuss that in more detail throughout the book?
Yeah. Well, there's a couple tools I have specific for outlier detection that I do cover in this section on interpretable outlier detection. One of them is called counts outlier detection, which is based on it's a simple idea, just based on multidimensional histograms, which, believe it or not, there weren't really other tools in Python taking that approach.
Okay.
Before. And so
it's novel in that way.
It's novel in that way, and it's useful. Having said that, I spend quite a lot more time looking at other techniques besides these, but I do think these are useful contributions to the field, and worth looking at. I mean, there's a reason I wrote them. The one's called Data Consistency Checker, and it's, as far as I know, a really unique approach to outlier detection. Like example would be, so again, it's for tabular data, that tool. If you have a feature that has values in it, like say 60.0, 70.0, 60.0, 65.0, and so on, and then you have one value and they all look like that, and there's a million rows, and then you have one value that's 65.2234. It has this unusual.
No, it's suddenly got. Yeah, it's got a different pattern.
Yeah, so it'll catch things like that, which most detectors would not. They would just look at the magnitude of the values and say, "Well, that's a fairly normal range of."
It's in a range.
It's a range that's
not
normal. Yeah.
It's not looking at the fact that everything else was rounded or whatever.
Yeah, exactly. So, and there's real world applications for that. Like, financial data would be an example too. If you see,
it looks like a human entry or something.
Yeah.
Versus, okay.
Yeah. So it could be like a value is estimated or negotiated or something like that. It's just unusual.
Yeah.
So it looks at the level of rounding in numbers. Or another example would be if you have two columns where one tends to be the product of or sum of the others or something like that. Oh, like say you have a column for before tax rate and the tax rate, and a third column for price with tax. So that third column should usually be the product of the other two.
Yeah.
But most outlier detectors, they would just check, is it roughly the same? But this would recognize the data consistency.
Is it exactly?
Yes, exactly. Yeah. So it'd flag anything, even if it's off by 5 or 10 cents, because there's some error there's some pattern there that varies. So it just has about 100 155, I think, tests along those lines that it checks for. Yeah.
Okay. Were there any concepts that you felt like, man, this is really hard to encapsulate inside the book, that you felt like, I want to include this, but it's going to be hard for me to explain it?
Surprisingly, no. Now, having said that, there's maybe some that were on the cutting room floor that that was the case. So I think in the end, we came up with, this is the set of material that is most relevant. So if you read this, you'll have an excellent understanding. It's fairly comprehensive. It doesn't leave out anything too important. There's maybe some things that could have gone in that didn't, that were maybe a little harder. But no, one of the interesting things is none of it is that hard. I think, the thing is just there's things you maybe wouldn't have thought of, or you might have forgotten.
Okay.
Related to outlier detection. It's fairly easy to do wrong. It's like with a prediction problem, if you create a model that's inaccurate, you cross-validate it, you say, oh, okay, it's not very accurate. Or if you do clustering, for example, you can look at how internally consistent are my clusters, how different are my clusters from each other. You kind of have a sense of how good your clustering is. But with outlier detection, you don't have these sort of easy ways to evaluate what you're flagging.
Yeah.
And consequently, if you do things wrong, it can be a little harder to realize that. So I kind of take through that, but mostly it's just kind of taking through the steps of what's involved with coming up with a good outlier detection system. And yeah, I think one of the interesting things is if you read it, pretty much everything in there is pretty agreeable. You just you maybe wouldn't have thought of it otherwise.
Yeah, cool. So if people are interested in checking it out right now, it's in the Manning Early Access program? That's
right, yeah. MEAP, yeah. MEAP, yeah.
Cool. And we'll include a link to it. How far along are you?
Well, I've handed in the first draft of the last chapter, so we're pretty close.
Oh, okay.
Yeah.
By the time this comes out, probably you'll have a few more chapters ready to go, and hopefully it'll be done soon.
I think so. We're looking probably a few months before it's completely ready. But in MEAP now, you get the first 8 chapters, which is about the first half of the book. So yeah, MEAPs are something I buy a lot too from when I buy books from Manning, just because they're cheaper, actually, to be honest.
It takes you a while to go through them too, right?
Yeah. So anyways, if you sign up now, you will get half the book now in about a few months, probably the rest of it.
Cool. So Brett, I have these questions I like to ask of everybody. And the first one is, what's something that you're excited about that's happening in the world of Python?
Well, I'm kind of thinking, because I actually did think about this before the show too. And I kind of feel bad because really I'm excited about these large language models, which is probably what everyone is excited about.
That's pretty common. Yeah.
Yeah. So I'm not an outlier in that way, not an outlier in a good way that way. But I mean, part of it is too, like I've worked with text processing and natural language processing for, 10, 11 years or something. So I think all of us that, have worked with it for that length of time, or especially people longer than that even, this was just unimaginable. What it's able to do.
Such a huge shift,
yeah,
right?
We would spend so much time trying to do, and now it's like, what now is like just trivial.
Yeah.
But, we were using 5 different libraries and creating all these ensembles of tools to try and do basic processing on documents. One project we worked on was working at analyzing contracts, and which we were often getting in PDF format. So in those days, the OCR was mixed. Yeah, I mean, because it's impressive how well it did work, but it was also frustrating how well it didn't.
Sure, yeah.
Yeah, so especially with numbers, because with letters, if you get it wrong, you can kind of tell by the context what the letter probably really is. But numbers, you have no context. If that's a 1 or a 9, you can't. You just get it wrong. Yeah, and just the amount of difficulty we had, doing these projects in those days, and now it's really, really remarkable.
Do you have a particular one that you're using?
No, ChatGPT, just because of the convenience of it. But
sure.
No, they're all kind of, the main ones coming out, Llama and Gemini, and the big ones are, it's a little hard to get your head around where some are stronger than others or weaker than others.
Yeah.
One project I'm working on now is trying to, figure out, take it sort of a gentle approach where you have a bunch of agents where some are good at certain things and others are good at other things, and trying to come up with a model that works on the whole as best as possible. So ensembling, if you will. But
makes sense. Yeah. So the next one is, what's something that you want to learn next? Again, this doesn't have to be about programming.
Well, the project I was just mentioning has to do with, ultimately it's having to do with climate change, which I'm trying to get my head around.
Sure.
As well. And so, I have a good science background, but I don't have a great background in climate or ecology and things like that. So, trying to understand that as well as possible. The app we're looking at it's an app people can use just on a personal basis. So, a simple example would be if you're just trying to make a purchasing decision. If I buy this or buy that, what are the sort of financial implications, health implications,
and impact?
Yeah, environmental, specifically climate. And well, a lot of life is just how you phrase things, right? So
sure.
Yeah, so we're just trying to figure good ways to people enjoy using it, because I think if we enjoy using it, we'll use it more, and also take its advice a little bit better and things like that. So.
Oh, cool. How can people follow the work that you do online?
Well, my LinkedIn would be one way. I do post there reasonably often, and if you want to check out the work I've done, my GitHub page, so I can give you links to both of those. I'm writing on Medium once in a while, but anytime I do, I'll post on LinkedIn, so you can just follow that.
Okay, that's a good general place. Okay, nice. Well, Brett, it's been fantastic talking to you. Thanks for coming on the show.
Oh, I was very, very, very glad you would have me. Yeah, thank you very much.
And I want to say thanks to APIlayer.com for sponsoring this episode. Use the code REALPython at checkout for your exclusive 50% discount. That's all caps, REALPython, no spaces. I want to thank Brett Kennedy for coming on the show this week. And I want to thank you for listening to the Real Python podcast. Make sure that you click that follow button in your podcast player. And if you see a subscribe button somewhere, remember that the Real Python podcast is free. If you like the show, please leave us a review. You can find show notes with links to all the topics we spoke about inside your podcast player or at realpython.com/podcast. And while you're there, you can leave us a question or a topic idea. I've been your host, Christopher Bailey, and look forward to talking to you soon.